So welcome back. I'm Janine Harrison-Chuck, Manager of Research, Communications and Marketing at the University of Manitoba. I'm here to introduce our next presenter, Dr. Feiyue Wang. He's an Associate Professor in the Department of Chemistry and also in the Department of Environment and Geography. He received his Bachelor of Science from Wuhan University in 1990 and earned his PhD in Environmental Geochemistry from China's Peking University. Dr. Wang joined the University of Manitoba in 2000, and in his academic career, he has published more than 60 papers in peer-reviewed journals and books. And if you become a graduate student at the U of M, you'll know what that means. It's quite significant. Dr. Wang studies how contaminants move about and interact with ecosystems and their inhabitants, with a particular emphasis on the Arctic and Himalaya regions. He spent a great deal of time in the Arctic on board a research icebreaker. If you like adventure science, and if conducting field experiments with polar bears lurking nearby seems appealing to you, then environment and geography may be the department for you. The topic of his studies is of a more somber tone: climate change and environmental degradation. Researchers like Wang are increasingly finding evidence to suggest the two are intimately linked. Will our planet one day come to recognize the one depicted in the blockbuster movie WALL-E, which I think you saw a bit of if you came in earlier? To find out, let's hear from Dr. Wang, whose presentation is titled WALL-E's Mission. Please welcome Dr. Feiyue Wang.
Well, thank you very much, Janine, and welcome to University of Manitoba, I guess. When I just turned off the movie, I heard, "Oh, no." So I think that word is probably much better than what I'm going to say. But what it doesn't have is, you know what? Some of you, when you watch these Disney movies, it does carry some scientific merit in it. And the message that I'm going to deliver to you is the scenario, as described in WALL-E, is not completely impossible. And in reality, if there's anything, that we could potentially be accelerating to that stage. So hopefully, I'm not kind of cause any depression in this room, but on the other hand, this also opens up a whole suite of opportunities for new mind, for new technology, new developing in science, engineering, and technology. So hopefully at the end of the talk, you will get a few inspirations, and that will be all worth it. So when people heard that yeah, you are an environmental scientist, but somehow when they introduce my department, I'm crossing between chemistry and environmental geography, which don't always talk to each other. And if you talk about chemistry, I believe all of you have learned chemistry in high school, right? And chemistry seems to be very molecular level, very kind of a small scale study. Whereas the environment seems to be, yeah, it's kind of green, and my work has indeed brought me to the Arctic, to the Himalaya. And so it seems to be it's two worlds apart. But in reality, the more you dig into it, the more you think about it, environmental scientist is actually taking the advantage or taking the tools, use the tools from almost every area, from science, from engineering, from technology, and actually we move even beyond that. It's crossing between the traditional natural science boundary and to even integrate with humanity there. So the first thing I would like to clarify is what the heck environmental science is, right? You guys do green, and what else do you do? So very often, people got confused, saying environmental scientist, yeah, you're an environmentalist. So in my first course, my first class of my second year university course, some of you probably will end up in that course. The first thing I tell the students is, I'm here to train environmental scientists, and I'm not here to train environmentalists. Any difference between the two? Any opinion? How an environmental scientist differs from environment? You can be both, let's say. But I consider myself an environmental scientist, not necessarily an environmentalist. So what's the fine line there? Yes? Exactly. I think that's actually a very good definition or distinction there. So what I call is here, of course, from elementary school, I have 2 young kids, right? And kids these days, this generation actually have much better environmental view than, let's say, well, myself is not that old. I shouldn't say my generation, but I'm getting old there. So at least the younger generation does have a better kind of environmental sense there. But just because we care about environment doesn't solve our problems. So the very first thing I would like to say is that environmental scientists need solid training in multiple disciplines to understand and mitigate complex environmental issues. It's fairly easy to say there's a problem. It's fairly easy to say, let's stop that, right? The solution to problem simply to cut off the sources. But in reality, things are not that easy. And we can always dream back to go 300, 500 years ago, but in reality, things cannot be changed. So we have to rely on a complicated, or an integrated understanding, appreciation of what's going on in the environment before we can say that we could actually help. I have another kind of a cartoon here to show the difference of what I call between an environmentalist and an environmental scientist is environmental scientists are not against technology, not against the science, not against the technology. And as you probably have experienced, or some of you will eventually discover, that in reality, environmental scientists are more and more becoming the driving force for the discovery, for the invention of new science, new technology, and new engineering. The reason I say that is, of course, the very reason that you are all here in this room, I assume, and I'm quite sure, I'm certain that all of you are science, engineering, technology kind of oriented, right? So when we talk about this, there are two types of Newton in you. The first one is the apple is falling. And you immediately ask, why it falls, right? And why it falls down, not up. So that's what I call the curiosity-driven research. It doesn't really matter to you, but you've seen the phenomena and you look into it. So that's the curiosity-driven research or thinking. And Newton could, well, we think Newton is very likely got all his ideas, all these discoveries because of this kind of a curiosity, but there's an equal chance that it happened this way. Newton was sitting there, the apple suddenly kind of crashed on him, right? So he just, what's the heck, what's going on? So he wanted to figure out why, and to stop apple from falling down. Of course, so far he hasn't been able to do that. But what I'm saying here is, as an environmental scientist, our research is driven by both curiosity and problem-solving approach. And to me, a very, very different kind of quality of a scientist is indeed by curiosity. And if we lose that kind of curiosity, I do not think that humanity will advance. But on the other hand, as an environmental scientist, very often you will find that your curiosity-driven research also bears a lot of implications. So in other words, it could also solve or potentially solve real-world problems. And then, of course, there are other, some of you, well, at least I recall when I was young, and I was reading something and I was doing some math, and we had a very nice talk earlier about math, and I thought I figured out an equation. And of course, I checked the textbook. It's been done 1,000 years ago. And the next day, I had another invention. Oh, this thing 300 years ago, it's already discovered. So basically, you start to complain, saying that life isn't fair, right? So if I were born 300 years ago or 500 years ago, I would become this big name associated with the textbook. The generations after me would learn my equations, right? So sometimes we feel that we kind of, the world has, there are not many kind of intriguing questions or technologies for us to discover. And all the neat things, all these important things seems to have been solved a long time ago. So all we have to do is we're basically punish the leftovers. And that's not entirely true. Yes, they may have figured out the most, I don't really think they solved it, but let's see. They may have solved to some extent those deep secrets of the universe, right? Nowadays we know much more about what's in the outer space and also what's in the very, very nanoscale, microscale universe. They may also have invented the most powerful machine, engines, cars, airplane, right? Name it. But the greatest ever question remains, And that is what my talk is about. How long can we call Earth home? Before you can do any invention, before you can do any thinking, right? As long as you're on this planet, you have to ask the question, 300 years from now or 100 years from now, are we still call this planet a home? Of course, the sound like that, you read lots of books about this, it's like very alarming, but, excuse me, increasingly we do see lots of negative possibilities, and we also see, of course, the urgent need in solve some of this problem. So I'm going to give a very quick overview of environmental issues, the current status. So of course, you all read lots of environmental related books, right? Newspaper, and you've seen this in Commonwealth. So if I ask you to name a few environmental problems, what would you tell me? Anyone? What environmental problem that bothers you the most, or that you've read the most about? Global warming? Yes. Anything else? Rainforest, deforestation, biodiversity loss, right? Anything else? Acid rain. Yes, we're lucky that we are in the prairie region, so it's not a major problem for us. But if you drive about an hour or two east, that's where acid rain has been kind of sorry? Clean energy, yes. Of course. Ozone depletion, exactly. Yeah, that's once again, when we talk about ozone depletion, do we see ozone depletion here in Winnipeg? No, we don't. Where do we see it? Australia? You need to go a little bit south. Remember, you're talking to somebody who works in those remote areas, right? I don't go to very populated places. I've seen large population. I was from China, right? So the only thing that attracts me is where you have less people now. And every time I go, I find less and less people. Antarctica. And that's where we think the answer is. That's where we think the warning science is. So if we look at the environment, so once again, another question to ask is, indeed of asking what are environmental problems, you can ask yourself, what are not environmental problems, right? You read the newspaper about the wars, about genocide, about poverty, about everything. If you really think about it, if you dig it further, it somehow links to the environment, right? To the supply of food, of resource, of water, of air, of anything that humanity needs. But in reality, if you really try to, as scientists, we of course we always list things, but you can also move one step beyond. In addition to listing everything, you can think about whether we could actually have a better understanding by grouping them. So to me, there are two major types of environmental problems. The question is, talked about biodiversity could be linked as the consequence of an environmental problem, right? So to me, there are two fundamental types of environmental problems. The first one is a direct habitat loss, right? So, of course, when I travel to the north, that's what I see. You fly to Inuvik, to Tuktoyaktuk, right? You look from airplane, and that's what you see. But with global warming, or if you can imagine that's 200 years ago in the prairies, which kind of situation was that? So when suddenly a landscape is changed from that kind of a pristine environment to a very, very engineered kind of a setting. So of course, we call this a major environmental problem because there's a direct loss of habitat to a variety of species, right? Of course, as a human, we think we got better habitat out of it, but from the environmental point of view, there's a price to pay. And the second type of environmental problem is simply chemical contamination. So you have a direct loss of the habitat. The habitat includes not only just land, but it could be water, it could be ocean, right? And the other one is the degradation, the quality changes. So once again, when we start to spray, when we start to use chemicals, those chemicals don't have to be from the laboratory. Some of these chemicals are perfectly natural, like trace metals, mercury. I'm a mercury person working with mercury. As far as I know, nobody in the lab is synthesizing mercury, right? Mercury is all, we dig out mercury from the earth. We redistribute them. So that's two types of environmental problems, but it takes different forms at different stage of human development. So here I have a timeline starting from 0. It's simply just a cheap one to start with. It's always easy, make the math easy, right? And so if we look at this one, so ever since the modern kind of history of a human society, environmental problems are there. That's from the very beginning, we have this overfarming issue. Not globally, but locally in different cultures, in different countries, different regions. Overfarming, of course, will result in habitat loss. The habitat, I'm using yellow color to denote habitat loss. And it could be urbanization and resource exploitation, right? So this particularly happens around 1850, and this is a landmark that we use in modern environmental science for a reason that I will discuss in the next slides or two. And then we have habitat loss due to pollution. The habitat is still there, but because of the chemicals, because of the either naturally occurring or anthropogenic chemicals, suddenly the habitat cannot be used anymore by the same species or same ecosystem, right? So if we talk about the contamination, and contamination is not a modern term, it's been there since the very beginning of a human society. Whenever a human interacts with the environment, there will be give and take, right? So it's a two-way traffic there. And we take things from the environment, we also somehow deposit or discharge stuff there. So the first thing that comes to mind is metal mining. So there's one school of view that the decline of the Roman Empire is actually due to metal poisoning. Mainly, it's still a very, very hot area. There are different schools of view, but this environmental kind of view actually is taking quite some weight in recent years. And of course, in the last 100, 200 years, particularly since the 1950s, that's when we talk about organic pollutants. How many of you read or heard of a book called The Silent Spring? Yes, there are quite a few. So that book, of course, is a landmark in modern environmental sciences, mainly pointing out the problem of DDT, or organic pesticides in the environment, right? So the problems, of course, still occurring locally, regionally, for some contaminants globally. Eutrophication. Anyone heard the term eutrophication? It's a very long name. Good. It's a very long name, right? Particularly for a guy like a Chinese guy, and eutrophication is quite a long word for me. But eutrophication was a major issue around 1950s, 1960s, around that period of time from Lake Erie. And as recent as now, some of you probably, your parents probably own cottages along Lake Winnipeg area. And the eutrophication is a big thing in Winnipeg, in Lake Winnipeg there. So we're saying Lake Winnipeg, some people are crying, saying that Lake Winnipeg is actually dying. And yes, indeed, there's enough reason to cause concern. So this question is quite recently, in the last 50 years. Acid rain was mentioned earlier, right? So once again, eastern part of Canada, or southeastern part of Canada, and northeast part of US is one of the world centers of acid rain, still to this day, although the situation is getting better, thanks to people like environmental scientists like my colleagues, right? Actually, there's a very strong linkage with UFM, acid rain, battle of acid rain. We have an experimental next area here. Anyone went to experimental next area? Yes, so it's just about 3 or 4 hours from here, right? It's absolutely in the middle of nowhere, but that's where a lot of neat stuff has been done there, including the cause and the consequence of acid rain. So eventually result in Canada-US agreement in abandoning sulfur dioxide and nitrogen oxides. Stratospheric ozone depletion, we just mentioned that earlier, right? So once again, we talk about ozone depletion. Ozone depletion is only a problem when it happens high. At the ground level, none of you want to have more ozone, guaranteed. It's a very strong oxidant, right? And of course, in recent years, we talk about emerging contaminants, endocrine disruptive chemicals, estrogens, those kind of things, pharmaceuticals, and radionuclides, particularly when we talk about alternative energy. So suddenly you start working with uranium, with those things. So Becker Lake, for example, in Manitoba, we potentially have quite some reserve of uranium. So uranium mine might actually come to Manitoba. So those are what I call past and present priority environmental issues. And their causes, of course, are rapid population growth fueled by cheap energy, And if you look at the population, right, anyone recognize this one? This happened not very long ago. Obama inauguration, right? So if you look at the population growth here, we see how population has changed from about 1 million years, that's the very early, that's the horizon of modern kind of a human species or Homo, and to the recent about as early as 20, I believe it is 1998. That's not because of me, I hope. It's population. So of course, we have a very large population driven by cheap energy, and relatively convenient technology could get this cheap energy to fuel our need. And the consequences, of course, biodiversity loss, we've mentioned that, talk about the changes in just loss, not just the loss of biodiversity, but it's also change in the ecosystem structure, right? Certain species are lost, and then you get some invasive species as well. Human health issues, as pollution, right? Water pollution, air pollution. And of course, climate change. Because to me, climate change itself is contamination. It's just contamination of the atmosphere, not by mercury, not by nitrogen, but by CO2, right? So we've managed to do a lot of things to the atmospheres, and because of the rapid development in the last 200 years. So this brings me to the next topic, and that's the main topic I was asked to present. I was told by Janine and a few other people saying that we're not talking about what's going on right now. Those people, they don't care what's going on right now because they're worried about what they want to do at the university, they want to do for their career. So I was asked to give you some kind of a picture of what's going on in the next 25 years. I don't know why they say specifically 25 years, not 20 years or 50 years. But anyway, that's my assignment. So this is my answer to that assignment. So if we can name one most important environmental issue, you will see it's not just environmental, but it will drive a variety almost everywhere in our society. That is the high amount of CO2, carbon dioxide in our atmosphere, right? So why is CO2 a concern? We heard they talk about, some of you mentioned global warming. So greenhouse gas effect, I assume everyone is fully aware of that. So simply because we are the very reason why we have a climate here is because we're exposed in between two light bulbs, right? One is far away, bright. What's that light bulb? That's the sun. And where's the other one? That's another one. The Earth itself, the Earth is a light bulb, right? And that's exactly how we're maintaining our surface energy, surface heat. So, of course, the solar radiation is a short wavelength radiation, could pass through the atmosphere, reach the ground, and then Earth as a black body, because the temperature is much lower, so the wavelength, the radiation has a much longer wavelength, and that wavelength, of course, will be emitted out to the space. But greenhouse gases like CO2 or methane, those gases, they actually absorb this non-wavelength radiation, so that this non-wavelength radiation from Earth light bulb does not emit out. As a result, it heats up our planet, right? So that's basically what the greenhouse gas effect is. Itself has nothing to do with the sun. It has nothing to do with that powerful light bulb. The only thing it does is the Earth. So what I'm saying is we're living in an atmosphere that has not been charged by the entire human history. And there are evidence to say that the Earth as a planet has not seen such an atmosphere in the past 35 million years, shortly after dinosaurs extincted. So there are evidence there. So this one here, I'm showing you a few kind of graphs like this. Any climate change talk will have a few slides like this one. So here we talk about the x-axis shows the time or 1,000 years before present. So of course, 0 means now, 2009, right? So extend to all the way to 2 million years ago. So from about 1 million to 2 million years ago, we don't really have direct data, but there are lots of model results we can draw upon. From about 800,000 years to now, we do have data. A good chunk of the data came from ice core. Anyone heard there's a huge lake in Antarctica? Lake Vostok, right? Thousands of meters underneath the ice. Has not been cut open yet. Basically, it's buried by 1,000 meters of ice, and that preserves a long, long history for our planet. So by taking ice core through in that region, not just from Lake Vostok, but from other regions of Greenland and Antarctica, we could actually read the past history. So the longest history that we have as of 2008, this was published in 2008. So it's very, very recent data. And any data like this immediately makes to Science and Nature. So those are the, as a scientist, that's our kind of holy grail. We want to publish our results there. So when you get there, so basically for the last 800,000 years, the concentration of CO2 in our atmosphere has been generally lower than 300 ppm parts per million in terms of volume. But if you look at the very end there, so it's a war there. Any of you watched the movie Inconvenient Truth by Al Gore, right? So Al was trying to make the point to actually stand on a lifter, try to reach that cliff of CO2. And indeed, because of this sudden change, you can see very, very small time frame and very rapid change. It actually results in a major change in your textbook. And some of you, well, I don't know how, my kids at the elementary school, they never had textbook, which has always worried me, because I was educated by the Chinese system. We always have nice textbooks there, right? So I don't know whether your textbook at grade 11, grade 12, which kind of textbook you use. But what do we think we're in terms of a geological time frame, right? And which epoch are we living? Sorry? We're actually a bit modern than that. From about, let's say, 11,000 years to now, the most recent epoch is called the Holocene, right? So for a long time, this whole period is defined as the Holocene. Starting about 11,000 years, you can see that's where the kind of CO2 concentration, I didn't show the earlier part, is actually increasing there. But because of this sudden change in recent years, and the textbook has been changed. So instead of calling we're in the Holocene, now we're saying that we're in a very, very different epoch. We're not in the Holocene anymore. We're in the new epoch called the Anthropocene. So the Anthropocene, basically, well, the name itself, what does this English word anthropo means to you? Has something to do with man, with human, right? So basically, we're talking about, because we talk about geological time scale. Normally, we talk about geological force, right? We talk about climate change. We talk about large-scale geological kind of phenomena. But here, for the first time, we're defining a geological time, which is remarkable. So if you look at the Anthropocene, we really talk about the last about 250 years, starting from 1850. So that's the period defined by the Industrial Revolution, starting from England, right, from Europe. And around 1950, humankind really made the history. The history is not broken. The record is not broken now. The record was broken in 1950. Ever since 1950, we've been living in this unknown territory. The CO2 concentration has been more than what the entire humanity has seen, or for the Earth for the last 35 million years. So because of that, we're saying every day is a new day for us. Because as a scientist or as a scholar, when we ask you what tomorrow looks like, you say, well, we go back, we look at history. That's why your teachers ask you to learn history, right? So read history, not just memorize all these names, all these years, but hopefully by reading history, you can know a bit about your future, right? Be a bit more smart, a bit wise. So of course, when we talk about what tomorrow looks like, what 25 years look like, we will say, well, before we can say that, let's go back to see what we have done, we've learned from the past. But if you look back, we have no reference there. For 35 million years, we've never seen a CO2 concentration this high. So what exactly will happen? We have no idea. So the And from 1950 to 2009, so we managed to increase the CO2 level to around very close to 400 parts per million now. And of course, as I mentioned, it's mainly because of the rapid growing human population and also because of the cheap energy, right? Energy source. And automobile, of course, define our current epoch. So the question is, what's going to happen when we look to the future? Because we don't really have any reference from the past, so we can't really go back to our own history to see what happened yesterday and will that be able to tell us tomorrow. So what's going to happen in the next, let's say in the next 50 to 100 years is we will see we're living in the consequence of a very high CO2 world that human has never seen. Global contamination and climate change are increasingly integrated, interlinked. So I'm just highlighting a few things as a statement or as a prediction. So climate change will result in dramatic alterations in habits and ecosystem structures. If we look about environmental point of view, we said there's habitat loss, right? So climate change, of course, will suddenly, we talk about the sea level rise, we talk about the melting of glaciers, so you will see a huge and dramatic alterations in habitats and ecosystem structures. High CO2 will result in ocean acidification. The global ocean, we're not just talking about lake acidification. When we talk about acid rain, we're worried about those shield lakes. Here we talk about the global ocean. We have data for about 100 years showing that indeed the average pH, the acidity of our ocean has been declining for almost 0.1 unit. 0.1 seems to be very small, but some of you will recognize that's a logarithm unit, right? And particularly what get me into this one is the global contamination is increasingly controlled by climate change-induced abiotic and biotic processes. What that means, traditionally, or in the last 250 years in our current epoch, pollution is mainly due to emission. So we discharge these bad things into the environment, right? If we want to stop it, we could easily, if we have the well, we could simply stop it. We could turn off the valve. That's the solution, right? But what we've seen, the sign into the future is, no. Even if we turn off all the valves, things will not change. Things will not improve in the near future. In other words, history has been written for a short while. That does not mean we shouldn't do anything. If we don't do anything, we will getting up into the warning stage, right? But what it tells us is that we have to do now dramatically to change things a bit after. We cannot change the next 30, 50 years. So both global contamination and climate change will result in accelerated destruction and degradation of biological human habitats. And the most important, as I mentioned, cutting pollution sources alone might not be sufficient anymore. And that's scary because it means that we lost the control, right? So what do we expect in 2035? Is that what we expect? How about this? Anyone watch this movie? There are quite a few very nice movies there. Of course, they're movies, but they do have some scientific merit in it. The Day After Tomorrow, that could, again, it has scientific basis in it. So what I'm saying is neither. I do not think in 2035 we will be at that stage. We will not be in either of this stage. But a lot will have to be done within this short period of time, within the next 20 years. This is key. We have to get a lot of things done within the next 20 years to change the course after. Because otherwise, we could end up in both of these scenarios. Why do I say that? Well, once again, to predict things, scientists had to predict all the way. We're trained to do prediction there. But every time you predict it, you know that there's a chance you will be wrong, right? And the last thing we want people to call us is call us to be wrong. But of course, when you have, with the education, with the disciplines, with the evidence you have, you can make some educated guess. The first thing we can do is, of course, as I mentioned, we look back. We see what happened in the past. But unfortunately, as I mentioned, there's nothing that there's no mirror there for us to look into the future. Instead, you have to look from other places. So what in the next 5 minutes, hopefully 5 minutes, I will take you to a tour to the Arctic. And that's where we think not only a lot of things are changing there, but most importantly, it is actually giving us the warning for the entire globe, not just on the top of the globe. So many of you, once again, in the media, in the movie, you've seen titles like this: Arctic meltdown, global warming, right? And a large chunk of glaciers suddenly got melted and collapsed away. And it's not just the newspaper reports anymore. It actually made its way to the highest podium, right? So in 2007, Al Gore and the IPCC, which is the Intergovernmental Panel of Climate Change, which is a group of scientists, they made all the way, they were awarded the Nobel Peace Prize for their work, for the message to the world that things are changing dramatically. So here I have a little kind of a movie clip. Some of you probably have seen this one. So what I have here is that white, kind of a bluish white, represents the sea ice coverage in the Arctic Ocean in the summertime. We know that in the winter, the Arctic Ocean is almost completely covered with sea ice, right? But I said almost because it's very different from lake ice, where lake ice is completely covered. Even in the high ocean, even in the Arctic, in the heart of the winter, you still have lots of cracks there, what we call the polynia or big leads. So of course, when summer approaches, some of the sea ice will be melted. So this is showing the summer minimum of sea ice coverage. And starting from 1990, you can see at this time we have quite large coverage of sea ice. But as time moves on, in the last 20-some years, we've seen dramatic decrease in the sea ice coverage, which is shown on the right panel of that graph here, shows the actual the surface area of the sea ice coverage in the summertime. So we've seen dramatic decrease in recent years. You can see by 2007, it's almost halfway down. So when we first started working in the Arctic around, for me, around early 2000, we're predicting by 2100, the Arctic Ocean will be sea ice free. And as of last year, we are saying it will be ice free as early as 2015 to 2030. So when we predicted 2100, I thought I will not see that day, right? So I don't have to worry. But now 2015, I think all of us will make it. So suddenly we see the entire Arctic Ocean that has not been melted for millions of years suddenly will be ice-free in the summertime. So why do we care? And immediately you have lots of economical kind of opportunities. The shipping route. Right now, you're shipping from Europe to China has to go through the Atlantic Ocean, passing through Panama Strait Canal, going through the Pacific Ocean. But right now, if the Arctic Ocean is actually open, so suddenly you can just tip over, right? So a lot of, from economic point of view, of course, good news. Churchill, believe it or not, it's the largest Arctic port in the world. So, and of course, there are lots of resources in the Arctic that has not been exploited because of the weather, because of accessibility. Here it simply shows the oil and gas resource potential. Surrounding the Arctic, you can see a lot of resources there. So you can see once the Arctic becomes it's warming up, it's more accessible. And believe it or not, a lot of these properties have been claimed. And industry they're always move ahead of the politicians, right? While people in Ottawa are still fighting, they already claimed their properties. So they're actually working on it. So just give you a appreciation of what's going in the Arctic. You can see Port of Churchill is situated at the very strategic location. And of course, who owns what? It's what we call geopolitics. So if you look at our map of Canada, we have this dashed line. If you extend them, miraculously, they intersect at North Pole. So basically we're saying the North Pole is cladding. And believe it or not, if you do the same thing with the US, with Russia, it's the same thing. They all claim North Pole is their property. So I'm not going into the details here. And of course, from my point of view, is more environmental than human health. So why is the Arctic Ocean not pristine? And how the Arctic ecosystem going to cope in the high CO2 world? Is there anything we can do about it? And most importantly, is the Arctic Ocean providing an early warning for the rest of the globe, right? So quick tour of, this is our main kind of research vessel. It's called CCGS Amazon, and lots of stories about it. I don't have time to share with you, but maybe we could chat later on. And the icebreaker is a modern research station. So it has inside, it's a floating laboratory. It has chemistry, biology, geology, satellite telecommunication. We also have a school on board program, so from grade 11 students could go to the ship to work with us, right? And he just shows some sampling device on the ship. And this is what we call the Christmas gathering in the Arctic Ocean, the whole town hall meeting. This is in just Christmas 2008. And we joke the population of the Arctic Ocean at that time is normally it's 1 to 80. This time we have 79. Normally we have 1. And that one person that day, of course, is very busy in the south, so he didn't show up. Santa. What we do, you do drilling, right? Pumping. We do lots of sampling there. Ice diving, so you can actually cut a hole through the ice, and then we have scuba diver. It's cool, eh? And we threw them there, and they do all kinds of sampling there. At the end, you hope they will be able to find that hole to come back, right? Sometimes they do get competed by seals. You can also pick flowers. So the winter of the heart of the Arctic Ocean, it's just beautiful. It's something look like this. It's just beautiful ice crystals and phenomena. The process of forming these flowers is still not well understood at all. And from contaminants point of view, from climate change point of view, actually we're thinking it plays a major role there. This my student Amanda is actually picking the flowers. So you do get pick flowers. And of course, while we're doing all the research, we also want to contribute to our geopolitical claim. So by doing that, we think the whole world will accept that indeed it is cladding. So the main message from the article, I'm not going into the scientific detail, but things are just a few kind of take-home messages. Things are not just happening, but are happening faster than anyone had thought. And we're predicting a seasonally open Arctic Ocean by 2015 to 2030. And we're also seeing the Arctic food web structures are changing. And even if we enforce the most strict control on CO2 emission, the climate for the next 30 to 50 years has already been written. We can't really change what's happening in the next 30 to 50 years. What we can do is we can change after. And the same is true for many contaminants, such as mercury. So even if we cut all the sources, we will still see contamination there. And actions are needed now to change the course for the future because it's too late. So is warming a fiction? I don't think so. Because for the CO2, for the atmosphere to be stable, we want the CO2 in our atmosphere to be around 350. And you see we've already way beyond that. And some of the scientists in this area are predicting that there is a point of no return. That means once we cross that point, we might not be able to reverse the course anymore. We might just go down the hill. So this point here is what is right now is estimated at 450. So how are we doing? The IUPAC, so not IUPAC, IPCC. You know I'm a chemist, right? So I have so IPCC projection is all way beyond this level. So that is so the scenario of warming. It's highly possible that we have abandoned our mothership. So what I call the humanity at the crossroad, we can do business as Euro. Humans continue to drive changes to the Earth system, somehow attempt to cope with impacts, or you can do part to sustainability, or we have to do some large-scale geoengineering. So each one, of course, comes with a price to pay. The first one, of course, I can guarantee some people say, well, climate change, the Earth will be destroyed. No. The Earth will stay intact without any problem. Earth has seen much higher CO2 but in the era before 35 million years. But what worries us is that we might not make it. And so the sustainability, of course, requires rapid and dramatic changes in the styles, in lifestyles, and the technology. So we're not talking about something we could do or we couldn't do, we shouldn't do. And geoengineering, we talk about large scale, so you can go to a spaceship while water is clean up for you, right? Or some kind of large scale geoengineering, the risk, of course, the risk of unintended serious effects. And how can we help warming? So I think the answer has to, we cannot simply say we just shut off everything. It has to be science, engineering, technology-based strategy toward what I call the deceleration. So we've been going through this great acceleration, and now economic crisis is telling us that we're probably going to a recession or depression. And indeed, we need that kind of a deceleration in development and in our relationship with the with the environment. So in terms of science, we need there's urgent need for better understanding of a complex, non-linear systems. Of course, we know DNA, we know microscopic world, but what really strikes us is a large, dynamic, non-linear system like the climate system, like the ecosystem. We need a better science of that. Technology, we really need a revolution in all kinds of technologies we're using. We need to look at the cleaner and the sustainable energy, as some of you mentioned. It has to be more efficient, and we have to rely on reuse and recycle. And engineering, there are lots of opportunities for there to do large scale of engineering. Of course, the risk is high, but we may not have other options. And of course, public awareness, policy, international collaboration is always important. So U of M collections, we actually, on this campus, we're working with most of these issues. I'm only showing you the climate and environmental change facility we're working on. I mentioned a few, right? That's our icebreaker, right? Was mainly with Laval University. We're the main users of the Arctic. We're also building an Arctic Ocean, miniature Arctic Ocean on this campus. It's a project I'm leading and should be there by 2010. So you will see a small ice ocean in Smart Park. And of course, we have a lab facility working on those issues. So with that, I hope that did not discourage you, but I hope that force you to think that changes are urgently needed, and it provides lots of opportunities in terms of science, engineering, and technology. Thank you very much. Sorry, running a bit late. Yeah. It's there. I think we have time for probably a short question, a few short questions. Yes.
The prevailing theory is that CO2 is caused by fossil fuel use. What effect do you think the end of oil will have on the rise of CO2 levels?
Well, the end of course, we talk about the oil kind of reserve, but the other thing is from if we're projection for the next 100 to 200 years, I think the fossil fuel will not run out. Petroleum, it might be, but coal, there are large reserve there. So I don't think it should be driven, the question should be driven by whether we have enough oil. It's about whether the trend we're seeing there and whether we have a need to actually maneuver that trend. Instead of crossing that point of no return, and we have to purposely deviate from the path that we've been taking in the last 50 years. Yes?
Would you agree that the biggest factor in the equation of trying to solve these problems will be the attitude of two countries, China and the United States?
Well, it's always easy to criticize other people. That's my kind of feeling. If we look, for example, as Canadian, I just finished a lecture in my own kind of undergrad class. As Canadians, we always say that we are small, we can't do much. If we look at the USA, they're much worse. But if you look at the data, look at the raw data, USA has been doing much better than Canada in the last 10, 15 years. Since when we said the USA has never signed on the Kyoto Protocol, but their kind of CO2 emission increase has been much less than what we have done in the last 15 years. In terms of China, yes, of course, China holds the key for our global environmental problems there. But the problem to me is it's not just China's problem. China is becoming the manufacturer base for almost the entire human population. So if you look at either as a base, a manufacturer base, or as a market, right? So what we need to do is, although yes, in Canada, even if we cut all the CO2 emission, we will not change much. But what we could do, we could, by developing new technology, we could help other countries to battle the problem. In the meantime, that provides us a huge market for economic development. So if any of you have a new kind of technology in terms of how to reduce CO2 emission from fossil fuel, and that technology will make you rich in China. Look at how big the market is, right? So I think the solution, if there's one way we can get out from the current economic crisis, that's true technological invention, and to apply those new technologies in other countries, in addition to what we're doing here in Canada.
You think coal technology is going to be
the technology is there. It's not. Sometimes politicians always say that, or industries always say there's no technology there. But from science point of view, those are actually, I didn't even mention this one because from science point of view, from technology point of view, it's there. It's simply just like this fuel efficient cars, right? They're not kind of in a lobo. They're there. The people are driving there simply because the market is not there, or the policy or the industry, right? They have not have the desire or the push to actually make that happen. It's not. I don't think it's a technological kind of a problem. But on the other hand, I do not think that holds the answer. I think we really need to look into non-fossil fuel because the trend I've shown there is climbing up very fast. If we think 450 parts per minute is the point of low return, we're going to cross that in the next 30 years. So maybe, sure. Yes, from one point of view, yes. From the total, China right now, since 2006, China surpassed the USA, becoming the largest CO2 emitter in the world. So that is a very good observation. But on the other hand, in terms of per capita, China is about 5 times less than Canada. So once again, so ultimately it becomes this kind of ethic or legal issue there, right? So shall we? Because of the large population base, shall we limit it? Okay, you have to be, the country total shouldn't be more than that, or we apply a universal kind of a per capita base. If that's the case, then Canada and the USA, we have a lot of job to do. We have a lot of house to clean before we can point fingers. At this time, I don't think pointing fingers is the best way to do. Sure. Yes. Yeah. Of course. Yes. Yes. Yes, yes. Yeah, actually, there's one facility in Saskatchewan. It's geoengineering. So once again, some of you, this is a SET, right? Science, Engineering, Technology. So there are a variety of technologies or proposals that have been, some are still in the proposal stage, some are already being used. In Saskatchewan, what they do is basically it's bury very, very deep of the ground. And there's another option is to actually bury CO2 at the bottom of the ocean. So those are two kinds of geoengineering. There's also ecosystem engineering by, some of you probably heard of that, by adding iron to the ocean, global ocean, to promote the photosynthesis, to promote the primary production. Because photosynthesis will consume CO2, right? And of course, those been tested, but in terms of the real output at this time is very, very limited because it's temporarily fixed the CO2 from the atmosphere, but when the algae die, and they get back to the system again. So we need to somehow kind of cap and isolate from being actively cycled within the environment. So that's the key, yes.
Do you think that carbon capture and sequestration is sort of passing the buck, though, to future generations? I know that it could be stable for millions of years, but what about if there are people living on Earth millions of years from now and geologic things happen that cause large amounts of CO2 that's been sequestered to be released?
Yes. Unfortunately, I think that's the way that we have to live with. That's what we call geoengineering. For example, not just CO2. You look at all this uranium mine, it is this nuclear power plants, right? So all this nuclear waste, how do they dispose those things? They're all buried on the ground. So through geoengineering, through modeling, of course, the also model could say a million years from now. But on the other hand, if we surpass that 450, we don't need to worry about a million years from now. We all need to worry about 100 years from now. Anyone remember WALL-E took place in which year? The movie shot starting from 2100. It took him 700 years to clean up. Eventually, there's one plant, green plant kind of took the road there. Yes?
I know that in Greenland they use the polypropylene blankets around the glacier melt plate to help the reflections. And it saves about like 2 feet of ice around. So do you think that's something that we should be using universally in the meantime to save the glacier?
I definitely think that there are immediate actions needed, but yeah, a blanket like that definitely will not solve the global picture, right? The global problem. But for example, from a contaminant point of view, I didn't get a chance to talk to that. The mercury concentration in blue gulf and the seals in the north are extremely high. And we start to worry about the health of those Aboriginal people. And our previous message has been, well, we just need to lobby the southern governments, saying that we have to cut mercury emission and then things will be okay. But our most recent finding is, no. Even if we cut mercury now, which the new president of the United States just signed on banning mercury, and even if we do that, the situation will not improve in the next 30, 50 years. So that's why we're calling the local community. They cannot rely on, they cannot just count on the South to change policy. They have to start adaptation now. That's the message. I think that's the same story as CO2. Even if we do everything now, things will not, the history for the next 30 years at least is already written, because that's what, there's a time, there's a feedback there. There's a time delay, time lag. So what we're seeing in the climate is caused by CO2 emitted very likely 30 years ago.
At this point, I'm going to have to cut things off with Dr. Wang.